Section: Introduction. In this section, we discuss the challenges posed by large language models, LLMs, particularly their tendency to produce hallucinations, responses that lack grounding in the source material. This unreliability makes it essential to detect these hallucinations effectively. Traditional methods for detecting hallucinations, like classification or ranking models, have been useful but often lack the interpretability needed to build user trust. With the growing use of LLMs, we have seen researchers explore their potential for hallucination detection. They have employed techniques such as chain-of-thought reasoning, fine-tuning large detection agents, and checking the consistency of responses from different LLMs. While these LLM-based methods offer interpretability, they also face latency issues due to their size and the computational demands of processing lengthy texts, which is a significant concern for real-time applications. To tackle this, we propose a new workflow that balances latency and interpretability. Our approach uses a small language model, SLM, for initial hallucination detection, followed by a larger LLM module, which we call a constrained reasoner, to explain the detected hallucinations. This two-step process is illustrated in our figures. Given that hallucinations occur infrequently in practice, the time spent using LLMs for reasoning about these texts is manageable. Our method also takes advantage of the existing reasoning capabilities of LLMs, reducing the need for extensive domain-specific data and costly fine-tuning. While previous studies have treated LLMs as complete solutions, we focus on their ability to explain the decisions made by smaller classifiers, showing promising results in non-reasoning tasks. Our framework aims to apply this concept effectively to hallucination detection. A potential challenge in combining SLM and LLM is the risk of inconsistency between the SLM's decisions and the LLM's explanations. Even models that generate explanations alongside their outputs can produce misaligned results. We address this inconsistency in our two-stage detection framework. Additionally, we analyze the reasoning of LLMs in relation to the decisions made by the SLM and the actual labels, highlighting how LLMs can serve as feedback mechanisms to refine detection processes. Our contributions include introducing the constrained reasoner for hallucination detection, which balances latency and interpretability, and providing a thorough analysis of the consistency between detection and explanation. We demonstrate the effectiveness of our approach using multiple open-source datasets. We define the grounding source as X and the model-generated hypotheses as Y, which consists of a series of responses. The generation process is represented as a function that maps the source to the responses. A response is considered hallucinated if it conflicts with or cannot be verified against the source. To balance latency and interpretability, we propose a two-stage framework. The SLM detects hallucinations, and the constrained reasoner provides explanations for those flagged. The detection process can be expressed as a function that takes the source and responses and outputs binary labels indicating whether each response is a hallucination. Only the responses identified as hallucinations are sent to the reasoning module, which generates explanations for them. However, even in models that rationalize their outputs, the reasoning may not always align with the detection results. We define the true intention behind the explanations and identify inconsistencies when the reasoning contradicts the detection. We focus on three aspects of consistency in our constrained reasoner. 1. Inconsistency identification. We create a mechanism for the LLM-based reasoner to indicate when it believes a hypothesis is not a hallucination, resulting in semi-structured explanations that include a free text reason and a flag indicating its judgment. 2. Inconsistency filtering. We explore filtering out inconsistent reasoning by assessing the reduction of inconsistencies after removing flagged explanations. 3. Reasoning feedback. We investigate the potential of the reasoner as a feedback tool to improve the detector by comparing flagged inconsistencies against the ground truth labels. Through these analyses, we aim to enhance the alignment between detection and explanation in our proposed framework. Section Summary. In this section, we propose a two-stage framework for hallucination detection that combines a small language model, SLM, for initial detection with a large language model, LLM, as a constrained reasoner, to to explain detected hallucinations, addressing the challenges of latency and interpretability. We also analyze the consistency between the SLM's decisions and the LLM's explanations, introducing mechanisms for identifying and filtering inconsistencies, and exploring the potential of the LLM to provide feedback for improving the detection process. Section: Experiment. In this section, we describe our experiment aimed at examining the consistency of reasoning within our hallucination detection framework and identifying effective methods to filter out inconsistencies. We also investigate how large language models, LLMs, can serve as feedback tools to enhance the detection process. We utilize GPT-4 Turbo as our reasoning model to clarify the rationale behind hallucination assessments, setting the temperature to 0 and the top P to 0.6. Our experiments are carried out on 4 datasets: NHNET, Fever, HalluQA, and Hallucim. We use the complete test set from NHNet, but due to the size of the other 3 datasets and limitations with GPT resources, we sample 3,000 examples from each of them. To mimic an imperfect classifier, we sample both hallucinated and non-hallucinated responses, treating the upstream label as hallucination. Thus, the actual hallucinated texts represent our true positive cases, while the non-hallucinated texts represent our false positive cases. The specific ratio of true to false positives is not crucial for our study, as we focus on the inconsistencies in the reasoning rather than the detection algorithm's performance. Human annotators evaluate whether each explanation genuinely clarifies why a hypothesis is considered a hallucination or if it justifies that the text should not be labeled as such. Our methodology centers on 3 main approaches, which we summarize in a table. The vanilla approach simply asks our reasoning model to explain why a text was flagged as a hallucination, without addressing how to manage inconsistencies. Since the explanations are free text, identifying inconsistencies can be challenging. If contradictory explanations arise, they may be shown to the user, potentially damaging trust and user experience. This approach serves as a baseline for comparison with our inconsistency filtering methods. The fallback approach introduces a flagging system, allowing the reasoning model to respond with unknown when it cannot provide a suitable explanation for a non-hallucination. This flag helps indicate potential inconsistencies, enabling developers to address them. The categorized approach refines this by using more specific categories of hallucinations, derived from real data analysis. One category, labeled as Hallu_12, signals inconsistencies when a non-hallucination is detected. By exposing the reasoning model to these detailed categories, we aim to improve its understanding of hallucinations and its ability to identify true cases. In our results and discussion, we present a table showing how well we identified real inconsistent reasonings using our flags. Both methods show strong precision, but the fallback approach struggles with recall, often missing inconsistent reasons. In contrast, the categorized approach successfully categorized most inconsistent reasonings under the Hallu_12 flag, making it easier to filter them for further use. When filtering reasonings with our designed flags, we effectively reduced inconsistencies between the upstream detection and our reasoning model. As expected, the vanilla approach had a high inconsistency rate. The fallback approach reduced inconsistencies but was limited by its low recall. The categorized approach, however, achieved a significant reduction across all datasets, with post-filtering rates as low as 0.1 to 1%, greatly improving workflow consistency. Our results indicate that the categorized approach shows strong potential as a feedback mechanism, outperforming the fallback method with high recall and achieving a macro average F1 score of 0.781. This suggests its effectiveness in accurately identifying false positives from the classifier, making it a promising area for further exploration. The high inconsistency rate in the categorized approach before filtering highlights the ability of LLMs like GPT to accurately identify true hallucinations when provided with refined categories, as indicated by the high F1 score. This suggests that LLMs can maintain accurate judgments without being easily influenced by specific instructions.